All right, so we're going to move right along into the application segment. And so when we're looking at exponential functions, you're either using a growth or decay model most of the time. So a growth model would look something like the green function over here, meaning that you have some sort of initial value. You have a rate of change, so that could be E, that could be like 1.05, like that's on the bottom over here. So really anything like that, and then it's going to be raised to a power. You may or may not have that constant K right there, but it will be raised to the power of time. Yeah, so that's exponential growth, and then right under that would be decay. And we already talked about how in the exponential function video that if you have a negative exponent, that turns it into a decay function. And so what that would look like, so exponential growth would be something like this, where it's increasing over time. And then exponential decay would be something like this. So it would be decreasing over time, which kind of makes sense because we talked about if you have a negative in front of the variable, it's going to flip over the y-axis, which is what you see there. All right, and so some examples of exponential growth would be really any population is typically going to grow exponentially. And compound and simple interest, I'm not going to do any examples with that because I personally find finance kind of boring, but you've probably seen that before. And some decay models would be radiocarbon dating, Newton's law of cooling, which you will maybe not see in the pre-cal class. So those are some common examples. Oh, also radiocarbon dating is a decay model, and we're going to do an example of that. So here's our first problem. We have a population of bacteria, and it grows according to the function f of t equals 200 times e to the power of 0.02 times t. And t is going to be measured in minutes. So we can see that it follows the growth formula here. So that is what the form is of that function. Like I said, I kind of just want to backtrack up here. This function down here in white, I am going to be using the first two because I think those are kind of easier to work with, but you might also have an initial value and then 1 plus or minus the rate, depending on if it's growth or decay. So if you had a 5% growth, you could do 1.05. So yeah, I just wanted to point that out, but we're going to be using the letter E. So for part A, what does the 0.0200 represent on the graph of this function? And so if we think about it, t is our independent variable. And if we plug in 0, that's going to be 0 minutes. And so at t equals 0, we have a value of 200. And this is modeling the population of bacteria. So this is basically telling us the initial amount of bacteria. And that's going to equal 200. So important to recognize that. I don't know why it keeps flashing like that. Can I nope, that just takes me to the next page. Okay. I'm just going to do it that way. Just click on the side. Anyways, okay. So part B, what is the concavity of this function and what does that mean in context? So we're going to have to graph this if we're going to figure out concavity. But we can do it sort of roughly. We don't need to have it be super exact in order to know what the concavity is. So I'll draw kind of this rough coordinate plane right here. And let's do red. So we do know that there's a point at 0, 200. So it's going to pass through this. And we also know that it's exponential growth. So we can kind of just draw it like this. Boom. All right. And we can see that it is concave up, like a cup. But we can't really think of it that way when we want to know what it means in context. And you might recall that when we talk about concavity, we're talking about the way that the slopes change. So as I move from left to right on this graph, if I draw my little tangent lines, you can see that it's becoming increasingly more positive. So the slopes on the left here are kind of flat, but then if you go all the way up here, they are very steep and positive. So, all right, so we know that the slopes are getting more and more positive. And we also know that slope is modeling basically the rate of change of this population. So we can say that the rate of growth of the population, that's a weird the. Sometimes this application lags. The rate of growth of the population is increasing. And that's kind of the definition of concave up, when your slopes are increasing versus the function itself. It's kind of a nuanced distinction, but that would be the definition. Okay, and so now we want to talk about domain and range. We do know that this is measured in time. We can't have negative time. Unless you know a way. I don't. If you want to like time travel. But that's kind of beyond the scope of this problem. So we would have a minimum time of 0 minutes, and it can go on until infinity. And then for the function itself, for range, f of t, we do know that we have that initial point at 0, 200. So we can't really use anything in the negative segment. So basically this entire branch right here kind of cancels out. So f of t is going to be from 200 to infinity. Infinite bacteria. And so that basically just tells us that our population is never going to be less than 200 if it's growing. Okay, and so at what time does the population reach 100,000 bacteria? So this is more algebraic. We have to just set the function equal to 100,000. And we had this initial value of 200. E to the 0.02 t. All right, so we would divide both sides by 200. You would get 500 on the left over here. And that's going to equal e to the power of 0.02 t. And so the next thing we want to do is take the natural logarithm of both sides. And that is because of the composition rule that we've talked about. So a natural logarithm, ln, is the same as log base e. So really what I'm doing is log base e of e. And whenever we see that combination, we know to cancel it out because of, undoing operations and inverses and whatnot. So this part is going to cancel out on the right, and we are going to be left with the natural log of 500. And then that exponent is going to come down. So we end up doing this a lot if we want to isolate a variable that's in the exponent. So we have that 0.02t, divide both sides by 0.02 to isolate the t. So I should explain at this point, we're trying to find the time at which the population is 100,000 bacteria. So if the population is 100,000, we have to set the function itself equal to that. And now we're just isolating for t. I know that an explanation does not come at the best time, but better late than never. And so t is going to be approximately 310.73 minutes.